Okay, we're going to do a really simple Kirchhoff's loop law example. So we're going to find the total current given all of these factors about the circuit. And it's really useful at this point to think about what way you're going to make your loop work, which direction you're going to work in. And a really quick rule of thumb is to look for the biggest voltage and make that your direction, and you're going to assume that you're walking in the same direction that this one is pushing the current. So we're going to say, well, our current is going to flow anti-clockwise, and then I'll draw it on so I can't get confused as I'm going around the circuit. Okay, and it's helpful as you walk around the circuit, it's helpful to imagine what's happening inside each component. So when I walk through the circuit, I'm going to be gaining that potential difference. I'm going to be gaining that 26 volts. I'm going to use it up as I walk through these. And then looking at this one, I'm going to be walking against the push of this circuit. So this is going to be a negative 2. Okay, I'm walking against the energy gain in that battery. And then, of course, I drop through the last one as well. And I'm going to take advantage of two things. One is that the sum of the voltages equals 0. And the second is that Ohm's law applies. And this allows me to sneak I in to a problem that's only got V's and R's. So some people like to separate out their loop according to type. So they do their EMFs, they do their voltages first, and then they do their resistors. Personally, I like to do it in the order that it appears, okay? It might be a bit messy when you write it down, but it means I won't forget anything, and that's really useful. So let's start with this one. So we're going to say, well, we have a positive 26 volt. Let's just move over so we've got enough room. We have a positive 26 volts going into the circuit. We're losing energy while we walk through the 24 ohm resistor. So we're going to say minus 24I. This being the voltage drop across that resistor. We're going to have another voltage drop through this one, minus 56I. This is also a minus 8. And this here, minus 10I. And that all adds up, just squeeze it on the end, to 0. Okay? At this point here, we've done all the physics. The rest is just maths, boring maths. Not even very interesting, exciting, requires your calculator maths. First of all, let's group together the numbers. So we've got 26 minus 8, we've got 18, and then we've got all these minuses, and it just so happens that minus 24, minus 56, minus 10 works out to 90, and that equals 0. Now, at this point, you're going, oh my God, she's going to end up with a negative current. What does that mean? And I hope that if you did that, you just sort of having a little mathematical moment, because I got to admit, when I looked at it, I was like, what's that minus sign doing there? But if you actually go through, if you don't try and skip any parts, you will see that that's actually a good thing. Okay, in a lot of textbooks, they don't do this. Oh, you can't actually see that, but I'll just rub that out and bring it up to the side. Okay, you'll just have to accept this. Over here, comes up here, and we get actually minus 90I equals minus 18. Okay, there's a minus sign there in front of the 90. There it is. Okay, which means I equals minus 18 over minus 90, and it just so happens that that works out to be 0.2 amps, 200 milliamps, okay? So a lot of textbooks will skip this, and you're left wondering what happened to that minus sign. It's still there. This is just mathematics. This is just rearranging, and here's our value that we get as a result of the physical imagining we did of a real system.